Thank you very much. It's a pleasure for us, Oshry and me, to be here in Santa Marta. We already made it as a tradition to come to this conference and give our lectures. We go to other conferences as well, but I must say that the number of friends that we have here and the colleagues that we find here is really overwhelming, and we are very thankful to the people of Magdalena that give us the support for our work. And I especially would like to thank the groups of Tecbaco and Banarica that gave us the support for the work that we have done on TR4, and now we are moving to new projects that Oshry, my colleague from Rahan Meristem, will explain. So again, thank you very much, and I must apologize that even though I'm here very often, my Spanish is not good enough to give this conversation in Spanish. So we'll try to do it as simple as we can. And I always like to start with the history of the project on TR4 resistance. And back, I would say, the genesis of this story starts when back in the 2010 approximately, the problem of TR4 started to become more and more pronounced in many parts of the world, and it moved outside the borders of Southeast Asia, and it started to become a problem first in Africa and the Middle East, and then later it migrated to the West. So just to recap on the history of this project and to give you some background about the project, what we did in the TR4 resistance is actually we created by a non-transgenic method a library of mutants. And we had a very large library of approximately between 10 to 15,000 mutants planted in our mutation, and you can see the library there. Each one of the plants differs from the rest of the plants in a small section of its genetic material, but without an intervention of genes from the outside. So this is not genetic engineering, this is not an intervention of nucleic acid from outside to the inside, but this is a simple mutation that does not really require any regulation for the product to be sold in any part of the world until now. And of course, we have a patent in many countries, including Colombia. We patented mainly the technology, but also the plants. For example, in Colombia, we have a patent on the plants that we created using this technology, and also we have a patent on the technology itself. And of course, we patented it in many parts of the world, anywhere from Australia to here. So in Africa and in the Middle East and everywhere where bananas are grown. So going back again to the history of this project, so the way we started the project, as I said before, we created this library of mutants, and the next step, we took the library of mutants for a first screen at the University of Wageningen at the laboratory of Professor Gert Kema, who is a nice friend and a colleague of mine. And I discussed the project with Professor Kema, and we decided to do it in a specific way where the first screen was done in a greenhouse, and the plants were inoculated with the disease on purpose. And Professor Kema happens to have a very large repertoire of the disease-causing organism, the Fusarium, and he infected the plants, all 15,000 plants, with a very large repertoire of Fusarium that he collected from all over the world in order to make this project not just applicable. And on the right is a repeat of exactly the same project, but we did it on a very special variety that was developed by us together with the tobacco group. And this was done on, we call it short Valerie or DR2, sorry. So in the second experiment, we got smarter. And what we did in order to achieve better results, we planted 2 plants per pot, expecting that one plant will be infected with the disease, and if the other plant is tolerant to the disease or is resistant to the disease, we will not see any symptoms. This gave us an assurance that what we see is really a good validation that the plant that is planted in the same pot with the plant that was symptomatic, this plant will really be most likely a resistant plant, at least in laboratory conditions. And at the bottom panels, you can see plants that are infected. So plants that really show the symptoms will show very large necrotic regions because of the high occurrence of the disease. And this is on purpose. It was done in order to not have many escapees from the treatment. So this was a very good news for us, because from approximately between 10 to 15,000 plants, we had in the first experiment about 453 plants that were, we call them asymptomatic. In other words, they did not have any symptoms. On the second experiment that we did, we also started with approximately 10,000 plants, and there we got, again, about 150 plants that were asymptomatic. Okay, with the first experiment, what we did in the next step, we said it's not good enough to see resistance in the greenhouse. We wanted to see resistance in the field, because the field conditions are very much different than what you see in a greenhouse. There is a stress of temperature and the lack of water and different types of stress that are inducive for the disease. So what you saw in the greenhouse is good for a first screen, but it's very important to continue with the screen in the field. And in fact, we found that it's really very important to continue with this screening process over and over in the field for several years. So you can see the first field experiment that was done, and this was done in the Philippines, in one of our production areas. We have a laboratory in the Philippines that gave us support for this. And in the Philippines, and many, I think, several of people that are sitting here came to visit the field trial in the Philippines. So I see people smiling and knowing that they came to see me in the Philippines showing this trial. And again, on the left side is another cycle of these plants. Again, in the field, we take the plants that successfully survived the conditions of infected field. We take them back to the laboratory, we repropagate them, and we produce a large population from each clone that was very resistant to the disease. and we plant them again in the field, and we did this time after time for several screening processes. So a very important part of our work was to realize that we're not doing this work academically. We're doing it for the growers, okay? So for the growers, it's important not only that the plant will be resistant to TR4 fusarium wilt, but that the plant will also have all of the parameters that are needed, that are important to the growers. These are yield and the quality of the fruit, number of fingers, how quickly the cycling is of fruits, and all of the parameters that are important to the growers. So we were very careful to make all of these measurements, and part of our selection was not only on the merits of being resistant to the disease, but we added all of the other traits that are important to the growers, realizing that we are doing this work as a real production project, and it's not only an academic project. So this is the second field trial in the Philippines, and what you can see here is that on the right side we planted all of the plants that showed resistance. This is all one field. And on the left side we planted the plants that were not resistant, or the descendant of the plants that were not resistant. And you can see clearly the difference between the right side and the left side, although there is a road in the middle, but before the road was put there, it's a contiguous field in the Philippines. So that clearly gave us a picture of our process. And here and there we received some of the plants on the right side that were infected, but the number of plants that were infected was not very high. While on the left side, 100% of the plants were totally susceptible to the disease. So this experiment, this is the second cycle, and it was very important. And actually, for me, this is the beginning of the field trials. This is not second field trial, but this is the beginning of the field trial, because from here, I had confidence that really our selection method and our mutagenesis really works. Okay, so this is the third field trial, and here we came back to coupling the plants in the field. So in each mat, separated by 30 centimeters, we put a resistant clone next to a control. And the control could be either a Williams or a gall that is not resistant to the disease, just a normal gall. And we planted them side by side, and we realized that the plants that were resistant were almost always resistant. There was a mistake of a very small amount of 0.3%. And the plants that were not or that were susceptible, of course, they remained susceptible. They did not miraculously become resistant. So this experiment, again, gave us a higher level of confidence that what we are doing in the field is really valid, and we can really claim that in our hands we have a good method for resistance of our plants to TR4. And it's important to mention that really before this experiment, I always related to the results, to the positive results of our work as really symptomatic and asymptomatic. But from this experiment and on, I think that it's fair to say that these plants are truly resistant to the disease and are not only asymptomatic. So you can see the different cyclings of selection that we did in the Philippines. So in the first cycle, we had 6.2% of the plants that we thought that were resistant. 6.2% of the plants showed that they were susceptible to the disease. On the second, once we did a whole full cycle of selection, we got 3.8. It's close to maybe 40% of what we got in the first selection. But when we did it on the third time, the number of plants or the percent of plants that were susceptible to the disease from the total population of selected plants was very, very low, was 0.8. And now we are continuing even with another cycle. The 6.2% of susceptible plants is acceptable when you have the disease, leave alone 0.8%, which is a very good result. And even if I compare it to transgenic plants that were produced in Australia, for example, they got more than 0.8% of SKPs that were selected as resistant, and in fact, they were susceptible. All right, so it's almost the conclusion of our project, and this project moved to the field in Magdalena in La Guajira. So La Guajira was infected. The first time was detected, I think, about 5 years ago or 6 years ago, something like that. 2008. 19. Okay, so it's about 6 years ago. Okay, so 6 years ago was the first occurrence or the first detection of TR4 in the West, actually, and that was in La Guajira. And so it was bad news for the growers here, and we felt really sorry about this. But for us, was really an opportunity to come and prove our effective way of selecting plants for resistance to the disease. And in La Guajira, we have two projects. We have one project on the old gall that was imported from the Philippines, but it's very important for us to redo the selection in the soils and environment of each location. And in this case, the location will be the location of Colombia. And of course, as I've mentioned before, very important for us was to repeat the experiment, and this was supported by our partner from Tecbaco, and to do the experiment in the Short Valley. And we are now 2 years after the initiation of these field trials, and we see basically similar results. The Valerie was not selected yet, but we are in the process now of getting the permission from ICA to bring back the selected plants to our laboratory in Rio Negro so we can perform the selection. While the gall is already selected, but we want to perform another selection under the condition and the environment of this area of Colombia. And I think I will show also, this is the results of our first field trial in the gall. So you can see that really, even though in the Philippines it was selected, some of the clones really did not give the good resistance as we saw in the Philippines due to the conditions of this area, probably the combination of stress conditions and the high occurrence of the disease. But you can see that, for example, 9560, in this clone, we had 0.8% of susceptibility, which is very, very good. So we are continuing to do this experiment thanks to to the support and to our partners here, especially Tecbaco and Bananero. Okay, so again, this is the short Valerie, and you can see the partitioning of the plants with accordance. This is before the first selection, and you can see the partitioning of the clones, that some clones showed actually very high infection level. This is something that was also obvious in the Philippines. But if you take the average of all of the population, you will see that really the level of infection is about, I would say, about 9%, 8 or 9%, while many of the clones show almost 0% infection or 0% susceptibility. So, of course, this is, again, the beginning of the second selection. So we will try from here, we will take the selected clones that showed high resistance back to the lab. We will produce a large population, and we will do it again to produce lines that have resistance, and it will be a true resistance to the disease. So in summary, what I would like to point out is that in the Philippines, after 3 rounds of selections, starting at 2018, we are showing now really a good level of resistance to the disease in the clones that we have selected. And in Colombia, we are still behind. We just started the experiment 2 years ago. We had some issues with regulations, which we appreciate very much, and we appreciate also the help of ICA and other groups in Colombia that really gave us the opportunity to bring the plants and take them to the field. So here I would like to finish my part, and I will give Oshry the opportunity to present 2 other projects that we are doing in our lab. One entails resistance to black Sigatoka. So we have the first lines of plants that are already in the Philippines. You will hear it from Oshry. And another project that we started just recently, due to climate changing and heating of our planet, we decided to make or to create a project for abiotic resistance in bananas. And the goal, or the overall goal, or the ultimate goal of our work will be to create a banana plant that has resistance to TR4, black Sigatoka, and also abiotic stresses. Thank you.
I will introduce you to 2 big projects that we are now working in Rahan. So the first one, as Eli said, is to develop a new banana variety that will be resistant, or at least tolerant, to the black Sigatoka. Now, in this project, we are using a different approach of mutagenesis. It's called direct mutagenesis or genome editing. And in this technology, we are doing a specific mutation in a specific gene that we have selected, that we believe that mutation in these genes will give us the resistance to the disease. Now, to do this process, we had to develop a very unique technology of what we call cell suspension. It's what you see here. These are individual cells of banana, starting from the flower of the banana. I won't go into all the details, but eventually we have these cells in the bottle, okay? And what we do next, we can take these cells and do the mutation on a single cell level. And again, this is a unique technology that we also do in Rahan Meristem. We can now take these cells and take all the process all the way back to a whole plant from a single cell. And now, because this plant was originated from this single cell, this new plant is now carrying the mutation that we gave him. And we can now use this plant for testing if we got the trait that we intended to. Now, this process of genome editing, it takes approximately 1 year in the lab from the cell suspension until the plant is ready for field. And during the last 2 years, we have selected many genes and did hundreds of plants using this process. These are pictures from our lab in Israel. And all of them are ready for field evaluation. Now, the big problem using this technology, or the bottleneck, is not the science, but actually it's the regulation. We have to go through really heavy regulation. In every country, we want to introduce these plants first for field trial and then for commercialization. So we did the first step for regulation in the Philippines. And after several months of negotiation and paperwork, we received the approval from the Bureau of Plant Industry of the Philippines. And they gave us the permission to bring these plants to the Philippines for field trial. Now, Philippines is heavily infected both with black Sigatoka and with Fusarium. So for the field trial, we had to find a plantation that is, on one hand, heavily infected by black Sigatoka, but is free from TR4, so we can check these plants. We already located a plantation, and we will start the field trials in the next weeks in the Philippines, screening for black Sigatoka resistance. And already we are not waiting for the result. We are already starting the regulatory problems also here in Colombia and in Latin America in general. We are collaborating with several regulatory representatives to solve this issue, so we will be able to do field trials also here. So to summarize, we perform genome editing with selected genes that we really carefully selected, and we believe that mutation in these genes will give us the resistance to the disease. We received a declaration from the Philippines that these plants are non-GMO, and we can introduce them, do the field trials, and then commercialize them. We plan to start the field trials soon. And of course, we are trying now working in a similar way with the local regulation authorities to receive the same permission, so we can do field trials here as well. And the second, or now it's already the third big project that we are working on, is to develop a new banana variety that will be resistant to the climate change, meaning the increasing temperature, the reduction in rainy days, and the salinity of the soil. You can see here an image, a prediction of the temperature in Colombia in the coming 50 years. And the increase in temperature will be very significant, and this will have a very big impact on banana production. Okay, so this is why we want to start this project now. So within a few years, we will have ready to tackle this issue. Okay, salinity soil also a very big problem. If we'll have a banana plants that can grow in salinity soils, it will increase the option for growing bananas all over the world. And again, we are using the exact same technology, but of genome editing. But this time, instead of choosing genes that are for black Sigatoka resistant, we are selecting genes that we believe are involved in regulation of the temperature stress, the drought stress, and the salinity of soil. Again, we already did all the process. We are expert in genome editing in bananas. We have many plants in our lab, and unlike TR4 and Sigatoka, this experiment selection we can do in Israel because we also suffer from the same climate change. And for that we are collaborating with Dr. Yotam Zait, which is an expert of banana physiology from the Hebrew University of Jerusalem. And he has a lot of sophisticated machines and technology. He can check photosynthesis, water content in the plant, water evaporation, and eventually all of this lead to production, to yield. So we already started the selection process in Israel and looking to see if the genome edited plant that we have created truly are resistant to the climate change. So again, we perform genome editing in selected genes to increase the banana tolerance to high temperature, to water stress, to salinity stress. We already started the first trials to evaluate our mutants. And again, like with the black Sigatoka, we're facing the same regulatory issue, but we are already done it in the Philippines, and we believe we can do it all over the world. It will take time, but I'm sure it will happen. And again, as Eli said, our final goal is to have the ultimate banana variety that will be TR4 resistant, black Sigatoka resistant, and climate resistant. So it will be easy to grow it all over the world. So last thing, I really have to say thank you to our team of scientists in Israel doing all of this hard work with the banana plants. Of course, thanks to Eli, who started all of this project many years ago, and really appreciate it, and thank you.